You want us to put it in scientific notation?
It doesn't matter either way. I think it probably will be in scientific notation. Yeah.
And it says the number, and then it says there's a blank space in 15, so.
So the first number it says is the coefficient.
Yeah.
And then
Okay.
10 raised to the whatever is after that on the far
I
right.
never used one of these little ones.
So we're just going to do a quick check here. Man.
So we live in I have my high school, so I don't. And then the one part of it, I think it was really good. I just had high schools, and I was like,
And so how did we do? Did you guys get those too? Sometimes I honestly want to know in case maybe I make a mistake. Did everybody get that? Yay! Did you get that, Jessica? No.
I don't know why. I got, for the second one, I got 6.09 times 10 to the negative 20. I don't
Yeah.
know.
Try the second one again.
Okay.
I think you're doing it right. And so it's
That-
this number
yeah.
times 3.
Okay,
Yep.
that's probably why. Okay. I
So-
think maybe my fingers are too big to press these buttons, maybe.
So Caitlin, we're doing an extra credit thing, and so do you have your calculator with you today? Because you can borrow one if you don't. And you can do it on a separate piece of paper or at the bottom of your homework. Did you get it too?
Yep.
Yeah, score. Okay.
Expectations are a little higher.
Oh, that's because I didn't time to find
Okay, so we're doing pretty good.
Now I got it.
Yay.
Well, no.
So we'll let Caitlin get set up, but I do have, what's that? Did you get it?
For both of them, I got.
Is it off by?
Exponent is one lower. This one's negative 24, and that one was 15.
Show me how you do it. I think I know. I've seen this before. I've seen this before.
6, 1, oh, wow, okay, that worked out. 6, 1, 0, 9,
No,
times.
don't you do it times.
Oh,
Yeah,
really?
so clear it, yep.
Okay.
So 6.09. And then your EXP key.
Oh.
Yep.
Okay, and then just do the negative 26 then?
Uh-huh. Yep.
Okay.
Perfect.
So in my calculator, you do the times 10 and then the exponent.
Uh-huh.
Okay, that makes
Yep.
sense.
And so this one was 14 also.
Okay.
That work?
Yeah, got it right
Yeah.
there.
Thank you. You're welcome. So Caitlin, I'm going to go on to the next one. Okay, so here's another one, guys. Let's see how we do with, oh, is this the same one? Okay. Well, dang. Okay, so Caitlin, I don't mean to pick on you, but, so go ahead and see what you can do. You guys cut this. Yeah. Did we get times 10 to the 14th?
Yeah.
Perfect. Okay, so at the bottom there, write down that number.
Okay.
And we'll talk about how you round things coming up. These you would not round. We're going to talk about that today, actually. These you would not round because the 7 and the 3 are probably exact. We're just assuming they're exact, so they bring no uncertainty. In case you're wondering. So it looks like this semester we'll kind of have options here and there to pick up points. So today we need to talk more about numbers. We talked about measurements in general on Friday, and today we're going to talk about numbers. Gotta love numbers. I was always thinking about numbers and science. To me, the two sciences that stand out are chemistry and physics, right? Numbers and science. Biology a little bit, but from what I've seen, people go into biology if they don't like numbers, quite frankly. When we measure something, of course, we give a value. That's the number part. And, of course, we'll also have units with, like I said, centimeters or inches or seconds or something like that. So the number part, actually, when we write the numbers, it's important that we write it correctly, relaying the correct number of significant figures. So figures are kind of like, to me, digits. Significant figures, significant digits. So you'll hear me abbreviate significant figures as SIG for significant, FIG for figures, sig figs. Okay. So this actually introduces something we're going to talk about here in a minute, this idea of uncertainty. Uncertainty to me is kind of like what it sounds like. It's like, I don't know. So the thing is, anytime you like measure something, there's a certain degree of, I don't know. It's actually a limitation usually in the device that you're using to measure it, whether it's a ruler or a balance. There's a little bit of wiggle actually at play in the last digit. Okay. So kind of related to that, whenever you measure something or you come up with a calculation where you used measured quantities that had kind of, but you can, in some cases, really go back to a known value and compare how close you are to the known value, how accurate your measurement or your calculation is, your accuracy. And I want to kind of contrast that to something called precision. Actually, in order to understand precision of your measurements, basically you have to do the measurement several times. When I worked in an environmental lab for years, and I was like, well, now why do you measure this quantity 4 times, 6 times, 10 times? Well, it's to kind of see if you can get the same value. You're like, why would you do that? You have a perfectly good value. Why do you do it 10 times? Well, if you see a scatter in your own value that you come up with, then you're like, oh, well, then there's a scatter to this analysis. And there is a scatter to every analysis, and that's called precision. Okay, and so accuracy and precision works pretty good with darts. So if the true value, if where you're trying to get is in the center, the bullseye, then here actually, if I were to average those 5 darts, it's not in the center. It's kind of off to the left, okay? So kind of if I would average them to check my accuracy isn't very good. My precision, like the scatter of the darts, again, I have a little bit of scatter there. There aren't any like off the board, which is good. My brother plays darts and he would like do good here, but okay. So with regard to darts now, notice in this scenario, I've got a nice tight fitting of my 5 darts. So my precision is awesome, but if my goal was to hit the bullseye, my accuracy stinks. Okay, so precision is really tight, accuracy is bad here. In this case, notice we've got them all nice tight, so my precision is great. I'm reproducible. I can repeat my answer, and it's right in the center. So both the precision is great and my accuracy is great, again, if my goal is to get in the bullseye. Okay, so that's kind of the difference between accuracy and precision. So again, a lot of times in the lab, you actually know what value you're after. So you can actually do kind of a quick subtraction and come up with the error of your weighs, no, come up with the error of your measurement, okay? So error, that's, there's a couple different ways to look at error, but error is associated with how did you get it to the target, okay? Error is associated with accuracy. Uncertainty, okay, is associated more with precision, okay? Again, just because you can get it in the bullseye once, can you do it 4 other times, right? Okay, again, back to the darts. What's the tightness of your analysis? And if you've ever sent away a sample for analysis, like to some other labs, like tell me what the iron content of this is, when they give you the results back, they will have to tell you how precise their method is, how their lab does with regard to that analysis. So error is how far you are from the true value, and uncertainty is kind of what your spread is. And uncertainty actually can be measured without knowing a true value, because what you do is you take the average as your true value and then just kind of see how far away you are from the average for each of your points. So there's different ways to talk about error. There's relative percent error, and then there's absolute error. Like I said, error is looking at kind of your accuracy, and you can do kind of a quick and dirty subtraction. Say, oh, you were higher than what the true value is, or you're lower than what the true value is. In labs, and I would imagine, this was a chemistry lab or environmental lab, I would imagine in all labs, they often send you performance samples. So basically somebody at maybe the EPA knows the real value of the sample they're sending you, and they just want to test how well you do with that sample. And then we can compare that to relative error or relative uncertainty. Okay, relative error then is not just a subtraction, and we might end up doing a percent relative error analysis in lab. But relative error says, all right, I have this difference from my value and the real value, and basically you divide it by the real value. Okay. Percent relative error. So like I said, and I'm going to kind of have to backtrack a little bit on this, but almost all quantities, did you need that last slide back there, Jessica?
What's the word?
What is that word? Okay. Almost all quantities have uncertainty with them. Oops. If it's a measured quantity, because some things you don't measure. Like one of the things in this room now, we have 6 people. Well, I guess I measured that by looking at it. But you're like, there's no wiggle in that because I have 6 people in this room. Okay, so, but usually there's a little bit of play in it. Like if you tell somebody what time it is, you're kind of estimating, maybe you're estimating to the nearest minutes or something like that. Okay, there's a little bit of play in it. Doesn't want to go. Okay, guess that one went. So the sig fig slide a few slides ago says you need to report a measured quantity with the correct number of significant digits. Okay. So actually, if we're following the rules that have been established for science, and there's a reason for this when we'll talk about why significant figures are so important, but it's like global, okay? So there'll be uncertainty, and it will always be in the last digit. So for instance, like a really practical thing is if you go to the store and you're buying hamburger, okay? So if you're buying hamburger, it might be like 1.3 pounds. Okay, the 1.3 is the number part, and the pounds is the unit part. See, it's not doing. Come on. 1.3 pounds. You can do it. There you go. Okay. So what we would say is they used a scale when they packaged it, and the last digit, which hopefully you guys are okay, the last digit is the 3 there. Okay. There actually is uncertainty in the 3, so I could put a question mark over that value in the tenths place. So here's 1.3, so it's 0.3 tenths. There's a bit of wiggle right there. That's basically the limitation of the scale that they used. Now, it would be kind of strange if I went to Walmart and instead of 1.3 is 1.36, oops, no, I guess it wouldn't be 6, 1.33257 pounds. You'd be like, dude, that is totally overkill, right? Okay. That means that actually their scale spit back a number, okay, that the uncertainty was clear out here in the 0.00001 place. You're like, dude, really? In general, this scale would cost a lot more than this scale, okay? But there's uncertainty in all measured quantities. And the way you write it from left to right, it's that rightmost digit that uncertainty is there. Okay, so again, there's no pounds necessarily associated with this. But what we say in this number, the 4.126 is certain. The 4.126 is certain. Okay, that value over there in the last place, that 7 in the 0.0001's place, is uncertain. And uncertainty or kind of wiggle or actually that's going to have to what we say propagate through your problem. When you go to relay something to somebody, it's important that you're actually telling them the truth with regard to how well you know that number. And that's actually going to come in with regard to rounding. It's sad today. Isn't that something? It is a Monday, you know. Okay.
I just went.
What's that? Okay, thanks. Thank you, I appreciate that. So in the lab, I'm going to talk about how do you look between lines and actually spit back a number. I'm going to make you the major lines, you have to kind of estimate between the major lines. So in this case, it's a balance. If we focus on the grams part, okay, notice that here's 10 grams, here's 5 grams. So each major line is 1 gram, right? So it looks like it's just past the 1 gram. And in this case, this person estimated about 2/10 past the 1 gram on its way to 2 grams. Okay, so this person, which I buy that, estimated it to 1.2 grams. Okay, so sometimes, and it's almost up to your own opinion. You might say 1.1 gram, and you'd be fine. And actually, that kind of makes the point. It's that you know the 1 for sure. The 0.2, 0.1, you're not really sure. So actually, in this case, I could put a question mark over the 0.2 part. The 1 is certain, the 10th part is not. So actually, when we do, when you guys collect data in your lab books, I will, for instance, in this case, I would put 1x grams. I am looking for a digit in both of these places, so kind of look for that in the lab. I'll tell you the format. So in this case, I think this is funny. It's like 1.2 and 1.26. Instead of a blue powder, we're measuring a pistachio, which kind of makes me hungry. On a different scale, okay, and the scales we have in lab are kind of nice. They're digital. But in this case, this is 1 gram, okay, 2 grams, 3 grams. So in that case, each of the divisions are 1/10. So we for sure can go 1.1, 1.2, and on our way to 1.3, okay. And in this case, the experimenter kind of looked, it's maybe 6 clicks. Okay, about 6/10 between that 0.2 and 0.3. So that's how they got 1.26. But in this case, do you see where the uncertainty begins there in the hundredths place? Okay, the 1 is certain, the 2 is certain, the digit 1 is certain, the digit 2 is certain. Okay. So it's kind of like looking between the gradations and estimating. So that's what you got to do. Do what you got to do. So I said all measured quantities bring uncertainty with them unless they fall into two broad categories of being exact numbers. So when I said there are 6 people in here, that's an exact number by counting. So by counting is exact. Another example of an exact number that brings no uncertainty is if it's by definition. It's just, it was defined that way. Okay?
You could look at the outlook of the classroom and you can say that there's 6 people by definition if you look at like the attendance and all that.
Yeah, that's true. I think so.
Just include the teacher.
Yeah. Yeah. But then there's like, for sure, right? Yeah, by definition. So pennies here, there are 7 pennies. It's not like there are 7 plus or minus 1 penny. Unless, but actually counting sometimes, like if you're counting like, 2,000 people, you could like insert some, you could have done it several times. You're like, I got to scatter in this. So I definitely have some uncertainty here, even though I'm counting, just because I can't count 1,000 people. Maybe they're moving or something like that. So this is a good example of by definition. So within the English system, of course, if we're measuring length, we can use a ruler like this. We can use length. And so if we were going to, like, if it was 1.3 inches, it'd be like, oh, the 0.3, then there must be uncertainty there. But within the English system, you guys would tell me that, I'll write it as what we call an equivalency statement using an equal sign. You guys would tell me that 1 foot is equal to how many inches? Yep, 12 inches. And that's just by definition. That's how they set up the system. Thank goodness. And so after that, if it's by definition, if that equality, 1 foot, is equal to 12 inches by definition, and it's exact, we will put exactly, or something like either exact or exactly. Okay, that's an exact relationship, I guess. It's probably more exact. By definition. The other day we talked about metric prefixes, and there's four metric prefixes you need to know. I said you need to know kilo. I said you need to know centi. I said you need to know milli. And I said you need to know micro. For this class, anyway. The others you might need to know for homework, but you can look them up. These you won't be able to look them up. But I bring this as an exact sort of relationship thing. So here we go. Let's pick on kilo, and let's do it this way. 1 kilometer is equal to how many meters? 1,000 meters, exactly. 1 kilometer is equal to 1,000 meters. And that's by definition. Kilo means 1,000 times the base unit. So that is exact. And things that are exact, what we call, these are examples of equalities. Equalities that are exact, actually, they're important to know if they're exact or if there's uncertainty. Okay? And I'll kind of show you why that is, probably on Wednesday. So this is such an important thing. Actually, I printed out this slide, and I went ahead and did numbers 1 through 5. So number 1 through 5. So one of the things that I'm going to hold you to is to be able, throughout the semester, to apply this particular concept of counting significant figures. So we have, let's see, this is week 2. Is week 2? Week 3? I don't know, it depends on how you count it. Kind of. But we have a few weeks left. So you probably want to know this. So when we look at a number and somebody says it's not an exact number, it's not, there is uncertainty in the number, then actually we can start this process for counting significant figures. Okay? So one is if you see a number, if you see a digit in your value that is non-zero, then that digit is significant. So an example of this is, if I had 1.396 centimeters, okay? According to rule number 1, and I use check marks to say it's significant. According to this rule, 1, 2, 3, 4, I would say I have 4 sig figs, significant figures.
What if it's like 1.03?
There's a rule for that. There's a rule for that. Okay? So 4 significant figures, 4 check marks. Now, the zeros are the issue. They really are. Oh, guys. So the zeros are the issue. So if that 0 is kind of between 2 non-zero digits, then it counts. So an example of that would be like 400.32. 400.32, let's give it grams. 400.32 grams. So according to the first rule, we would go, the 4 is significant, the 3 and the 2 are significant, and according to the second rule, I have to count those 2 zeros as significant. So how many sig figs do we have?
5.
Yep, 5 sig figs. Cool. So we still have a few things about zeros. So this is a trailing 0 after the decimal place. A trailing 0 after the decimal place. Let me show you an example of that. Let's see, what if we did 105.300? Okay. So I got the 1 is significant, the 5 is significant, and the 3 is significant because of rule 1. This 0 right here is significant because of the second rule. And now these zeros are significant because they're trailing zeros after the decimal. If we go back to the hamburger thing at Walmart or whatever, okay, or wherever you buy your hamburger, this would say that I have a scale that actually weighs out to the nearest point 001. Okay, so I have a fancy scale. And so those trailing zeros after the decimal are significant. Any questions about that? Okay. Leading zeros are never significant. Let's see. Oh yeah, okay, an example of that. So here is a very small number. Leading 0, this rule right here, actually rule number 4 deals with small numbers. So in this case we have point, and I usually put I put a 0 there. This is not the leading 0. This is just a 0 before my decimal to show I'm using a small number. Okay, 0.0005070. Okay, 0.0005070. So let's go back, applying the first rule, the 5 and the 7, significant. Applying the second rule, that 0 between the 5 and the 7, significant. Applying the next rule, that trailing 0 after the 7 is significant. Applying this rule, here we go, X's, X's, X's. Now, it's important, and sometimes I try to convey this to students who haven't necessarily kind of played around with numbers in science. It's very important that we put these zeros there, because that number is totally different than 0.5070. Though these are not the same numbers, okay? But they don't bring, and I'll try to convince you of this, these leading zeros they don't bring any uncertainty to it. I'll try to kind of show you how that works. So you have to put them there. They're important, but they don't count as significant digits or significant figures. Okay. The last one, actually, I'm going to kind of come back to this one. The other day, I think I asked you if, I think we had a number, and it'll be a big number. This last one deals with big numbers. What if I had 350,200? 350,200. So you guys would tell me the decimal is right here. And remember the other day I said if you don't put the decimal there, it's implied. So you guys would tell me, and we're going to actually kind of, like I said, kind of revisit this. So I can put a decimal there, that's because where you would tell me it is, and I put dashes around it to actually show that that is implied. It's called an implied decimal. Just because we know it's all there, but no one really put it there. Okay. Those zeros are, it's a little ambiguous. Because we don't know, for instance, if the uncertainty begins here or here. Revisiting this, by the way, counting sig figs, you know for sure the 3 and the 5 and the 2 and that 0, you know for sure that those are significant. You for sure know that. I guess I should put a question mark over the 2. We don't know whether the uncertainty begins at the hundreds, the tens, or the ones. We're just like, yeah. And the word ambiguous means like they can't nail you down, kind of, if you're ambiguous. So we'll kind of come back and revisit that here in a minute. Okay, so significant figures are important. So do you guys have the answers to these? Okay, so I'll let you go ahead and count those up right quick. So you can kind of go ahead and check your answers. How'd we do? Any questions about those? Yes.
Why is 2.503? I got 2.
Okay. The trailing 0 after the decimal, so that's like rule number 3.
I thought it meant like at least 2 when you said trailing.
Okay.
Like it meant like it had to be at least 2.
Nope.
At least 2 zeros or something.
Nope. Trailing 0, it could just be 1, so that's why. Yep. Sounds like you got it now though, right?
Yeah.
Cool. We good with all that? Okay, cool. So here's where I'm going to convince you maybe of a few things. So if we, for instance, said that these are pounds, you know, say it's hamburger, okay, you guys would tell me probably this third scale costs a lot more money, right? Because it can actually measure farther down than the top scale. But the reason these are significant is if we assume, and it's kind of, I don't know, if you really get into the analytics of everything, it's not necessarily plus or minus 1. But if we kind of assume the play in the uncertain number that has a question mark is plus or minus 1 of those units. So for instance, in the case of 2.5, it's really plus or minus 0.1. In the case of 2.50, it's plus or minus 0.01. And in the case of 2.500, it's plus or minus 0.001. Kind of the wiggle in that last digit. Because remember, like that last value, 2.500, somebody really can actually, the uncertainty begins in that after that last 0. Okay. Then if we go ahead and come up with, that's what we call the absolute uncertainty. If we come up with a relative uncertainty, which is simply the value divided by the absolute uncertainty, we get 1 in 25 parts for the first one, we get 1 in 250 parts for the second one, and we get 1 in 2,500 parts in the last one. So here we say, or we can see that the relative uncertainty is definitely affected by having those trailing zeros after the decimal. So here's where now we're going to apply a similar logic, and we are going to look at those, what are they called? Leading zeros. Okay. So leading zeros, just to remind you, remember leading zeros is that small number. So if you have a 0.0000502 or something like that, you have to put those leading zeros in there to kind of show magnitude. But I'm going to show you, even though they're an important part of your answer, because they show kind of magnitude, they actually, those values, those trailing zeros don't bring any more to your relative uncertainty. Okay, so here's what that looks like. So let's pick on 25. Okay, so we have 25, we have 2.5, we have 0.25, we have 0.025, and we have 0.0000025. Now, in all of those cases, how many sig figs do you have? 2 sig figs in all of those cases. And you'd be like, Mrs. Snipes, that doesn't quite seem fair. Because we know that the balance that weighs this one is a lot more expensive than the balance that weighs this one. But we're talking about two different magnitudes of numbers. Okay, so I'm gonna, I don't know if I can't remember if I talked through it or not, my next slide. But if you were to do a similar thing that we did on the last slide about trailing zeros after the decimal, you would come up with the relative uncertainty is 1 in 25 parts for all of these. 1 in 25 parts. Bottom line. Okay. So let's revisit that last rule. That last rule number 5, the what is it? Trailing zeros before an implied decimal. So if we pick on the number 32,000, and somebody says it's a measured quantity, so there's uncertainty, do you guys buy this, that, you know, the measuring device could actually have uncertainty there in the first, where the 2 is, which is the 1,000ths place, okay? Or it could be right here. Oh, by the way, if that's the case, then it has 2 sig figs. If the uncertainty is here, it's 3 sig figs. The uncertainty here, it's 4 sig figs. Uncertainty here, it's 5 sig figs. So it's kind of like, I don't know. All right? So it's ambiguous. So in general, and I'll kind of show you how you can get around this, but if you have a number like 32,000, we just assume that it's the fewest number of significant digits possible, which was 2. We assume that the uncertainty begins there in this case, the thousands place. Similarly, the convention is if somebody really cares, now this decimal turned from implied to explicit, so I'll kind of put the word up there. This decimal is explicit. And sometimes we'll be working problems and they'll give a measured quantity and they'll put a 0 there after what otherwise would have been kind of ambiguous. They will put an explicit decimal. And the kind of convention is, in that case, then they are telling you, they took the time to tell you that the one digit that's uncertainty is that last one in the ones place. So this is back to 5 sig figs. Okay, so I think I got ahead of myself. If we do another example of that, the trailing zeros before an implied decimal place, how many sig figs do you think this number would have? What if it's 107, comma, 500? Okay, and the decimal is just implied. It's not really put. 4 sig figs. Yep. Very good. So one of the things that my slide is missing, so on this slide, if you want to, you can add this. If you have a number that's packed up in scientific notation, then actually the first part, that coefficient part, the part that's between 1 and 10, that part is what tells you significant figures, okay? So in scientific notation, I'll put psi, NOT for notation, the coefficient equals sig figs. How's that? We really have to be. So remember, the coefficient is that, like I said, that first part. So what if we had 5.30 times 10 raised to the 5th? Okay, so how many sig figs? 3. Yep. 3 sig figs. So we're going to look at that same number again. I think that 320,000. And we're going to see how we can kind of clean it up using scientific notation. So I think one of your homeworks that you guys did, I think you had some work at unpacking that 3.2 times 10 to the 4th. If I unpacked it, I would move it 1, 2, 3, 4. So that would make it 3, 2, 0, 0, 0? Thank you. So those two numbers are the same, right? But packed up this way, can you see, like the slide said, there's 2 sig figs. So 32,000, we could also write it 3.20 times 10 to the 4th, still 32,000, right? But now, of course, it's 3 significant figures. We could write it 3.200. It's 4 significant figures. And last but not least, this one just kind of floors me. We could write it's 3.2000 times 10 to the 4th, and that's 5 sig figs. But otherwise, you could write it as 32000 with a decimal. That's also 5 sig figs. Okay, it's the same thing. Cool. Okay, so let's take a look at these right quick. This will be due on Wednesday. And here's what it looks like. I think I just did it. These are 2, oh man. I win. All right. So, not too bad. This is kind of the convention that we did before. It says underline zeros that are significant and draw an X through zeros that are not. Question 43, you have the answers to in the back of your book, so you should do fine with this. The next one looks like this. How many significant figures are there? Not too bad. If you were me, I would kind of do check marks, kind of. And actually, on your unit. If this works for you, which I hope it does, on your Unit 1 exam, you're going to have a little section that says count significant figures. The next one looks like this. Some of these are right, some of these are not. So in that last column, for instance, B doesn't look right to me, right? 5.6 times 10 negative 12 seconds has 3 sig figs, so you'll just fix B. The last one, though, I want to mention something about, because actually we haven't talked about rounding, and this one you have to round. I bet you guys are all pretty good at this, or have been exposed to this. So for instance, if I had a problem like, 53.21 5, 9, and somebody told me, like this problem, that I could only have 3 significant figures, okay? What I would do is start from left to right. I would pick off my 3 significant figures. I have to round it to 3. I think they want 3 significant figures in this. Okay, so I would truncate my number right there. Now the question becomes, how do I round the darn thing? And if you guys are probably pretty good at knowing that if this number, which is past the digit where you want to run, to where you want to cut it, if it's greater than or equal to 5, then round up. Okay, so the fact that this is a 1, if I'm going with 3 sig figs, what will my number be? Yep, 53.2, I agree. So 53.2 will be your number. Okay? All right then. Awesome. See you on Wednesday.